Warning! Tube amplifiers have lethal voltages inside them. Please do not attempt to build, test, or repair these without understanding and following all safety protocols. Hey y'all! Here for round 2 of the 47 amp. This one is mostly going to be on the laptop looking at schematic, how I develop a plan of action, and I use what's called R&D, which is rip off and duplicate. And I look for something that's very similar to what I want to build and kind of copy the starting point from that and then add my own refinements to it. And you'll see as I go through the schematic how I do that and how we determine the operating points for the tubes and then calculate up the power needs, go through some software that helps decide what kind of transformer we need, then go look up the parts online, find what will work for our project, and order them. So without any further ado, let's jump into the schematic. Okay, I'm going to walk you through my process of creating a new amplifier, and while we are going to be designing it, I usually don't start from scratch. Like I said, none of this stuff is new. People have been building these kind of amplifiers for decades, and so there's no point in totally starting from scratch on how you want to build it. So I looked online, and while I didn't find a lot of these, I found this amp where someone was using a 27 driving a 47, which is what we're going to be doing. And so here is what they did. They ran the plate voltage at 186. We're going to be running it closer to 250. And I will explain why in a minute. It's capacitor coupled to a 27 that's running at 91 volts on the plate, which is a lot lower than I'm planning on running it. They're driving in that with a 57 triode strapped that's capacitor coupled to the 27. And like I said in the other video, if we need to get the drive up to increase the input sensitivity, we're probably going to use a 56, which is a triode by itself instead of a triode strapped 57. We don't need 300 millivolts RMS sensitivity. 2 volts RMS sensitivity will be fine, which I'm hoping will drive the 27 without needing the extra stage. But if we do, we can add it. So to start with, we're going to be doing this section of the amplifier with the 27 tube and the 47 tube. So we've decided we're going to use these 2 tubes, but we need to keep in mind we possibly will be running this tube in addition to it. And so let's look at the specs on some of these tubes. Here's the 27, and we can see here that the plate current is 5 milliamps, is what they're suggesting. You kind of limit it in that range. And on these older RCA manuals, this is the RCA 10 tube manual, which you can find online. It has a ton of good information at the front of it, showing circuits, biasing, just really neat stuff, because in these early days, these manuals helped sell the tubes, and so they gave a lot of information, circuit designs, etc., that really help you in designing an amplifier or modifying an existing one to do what you want it to. So we see here that at minus 9 volts, 135 volts on the plate, we got 4.5 milliamps of plate current. And it's telling you the plate resistance. Here's the amplification factor, stays at 9 across the board. And this looks like a good spot that I want to run this tube in. Also note we got 1.75 amps of heater current, which is quite a bit. And it's also at 2.5 volts. So we write all that stuff down. Then we scroll down here to the plate curves. And what I look at here, the plate curves run at an angle about like this. And without getting into, drawing everything out in detail, what I do is I look at the operating point, or where they bias it at with no signal. Now, the circuit we saw, they were suggesting to bias it about right here at 9 volts, but way down here on the curve. And while this is okay, to me it looks more linear moving it up the curve to about this point, which is close to 135 volts that they suggest in the tube manual to bias the tube at. And as you can see here, we got a lot more headroom, and to me the tube looks more linear up in this range. And by that I mean the gaps between these lines are even. And so that's why we're going to bias this tube instead of at 90 volts on the plate, 135. And what that means is we're talking about the voltage across the tube, not the B plus going to that stage of the amplifier. That doesn't include the voltage drop across the plate load resistor. So we're going to probably be putting over 200 volts on the plate load resistor, which is going to work out fine because in this amp we're going to be running the output tube hotter than what that schematic's showing. So now I'm going to scroll down to our next tube, which is the 47. And let me show you this too. These tube manuals, they have these charts that show you all kinds of information on the different tubes. It helps you choose between the tubes and what you would like to do with it. And like this is showing you the suggested operating points for these tubes. And very, very, very helpful in trying to figure out how to set up tubes and how to set up an amplifier. So here's our 47. And here are the characteristics for it. Once again, we got 2.5 volts. We got 1.75 milliamperes. 250 max on the screen and the plate. Now remember, this is across the tubes. So if we're running the grid at 16.5 volts, that means we can run the plate at like 265 or 266, at the max. And so running it at 250 volts, we're not actually up against the limit because we've got this 16 volts of headroom for the voltage drop across the grid. Now, if we do decide to run this as a fixed bias and put negative voltage on the grid to bias it, which we may be doing, then we will have to respect this 250 volt max because we're going to be grounding the grid. We'll get more into that later. Here's the other thing you want to write down is this 31 milliamps that this tube can be run at. And we're going to be using these to calculate up what type of power transformer we need to look for. The other thing you want to look at is this load resistance, which is telling you the output transformer impedance that this tube wants to see. So we're going to scroll down here, and here's some more information about the tubes, on how to bias it. And then here's the plate load for this tube. And they've drawn in the 7K ohm line for us. And as you can see, if you bias this thing right at 250 volts at negative 15, you've got a nice linear response across the range as this tube swings. And to get everything out of this tube, you're going to need to swing right at 30 volts peak to peak. to get everything this tube has. So we're going to be biasing this tube right there. So now we're going to go down to the last tube, which is our 56. And as you can see, we're at 2.5 volts still on the heater, but this one's only 1 amp. So that's going to take some load off of our requirements for the heater filaments in the transformer. Again, this one will handle 250 volts max. They're saying, to set the bias at negative 13 volts, which we probably aren't going to be doing on this tube if we ended up using it for a driver. So let's go down here and look at its curves. And as we can see, this is another very linear tube. Look how even the gaps are across these curves, which is what you're looking for in an audio tube. But this time, we know if we're using it on the input of the amp, we're probably going to have at the most 6 volts peak to peak, and probably less than that. So if we look at this curve chart, and we look at our 5 milliamps limit, and we're talking about running around 3 volts negative bias, we're probably going to want about 90 volts on the plate, which would get us to this bias point about right here, and then it can swing back and forth across this. And as you can see, we can easily get the swing we need at that bias point to drive the following tube if we need to use the 56. So again, these tube manuals or the tube data sheets really give us a lot of good info that we can use. And again, see here they're showing you how to do a resistance coupled audio frequency amplifier. And they're showing you how to do the plate load resistor, how to do the heaters, and all that stuff. So there's a ton of good charts in here and schematics and ideas to use. And this manual was probably written in the 1930s, almost 100 years ago. So again, there is no reason to be reinventing the wheel as we're coming up with these schematics. So we're back to the schematic. So we're going to be changing a lot of these values, and like we are not doing, here's the power supply they did. We're not doing anything like this. Doing something totally different. And we know we're going to be running closer to 250 volts here. We're going to be running like 135 volts here with the same bias on both ends of this. And then this tube here, we're probably going to be running very close to this. We're going to be running about 90 volts on the plate and running, 3 to 4 volts negative bias on the cathode. So the other thing that I note in this schematic that I see problematic is there's no decoupling between the output stage, this driver stage, and this driver stage. And so we're going to be adding, out of necessity, since we're going to be running lower voltage here and here, we're going to also be adding a resistor, capacitor, and then a resistor and capacitor to decouple these plates all from each other. And potentially, they've got global negative feedback going across the whole amp like this, which is something we could think about doing. But we could also run some plate-to-plate shade feedback across these two tubes here to calm down this pentode. Also, they're running this in straight pentode mode. We're going to be running this in ultralinear mode off a tap on the transformer. So we're not going to need near the amount of negative feedback that this amp required to get the distortion in check. Another option we could do on this 27 is what Andy Evans on DIY Audio has been playing around with these 26 tubes in a preamp. And when I was talking about earlier, potentially using a choke plate load on the 27 tube to try to get the drive up enough where we can make this a single stage amplifier, this is what I was talking about doing. And here he's got his plate choke instead of the plate load resistor, capacitor coupled, and then here he's used 10 LEDs to get to this bias point, which is another possibility. Instead of using a resistor with a bypass cap, is running diodes in series to get the voltage where we need to be to bias the tube correctly. So this is another option of some things we can play with. So here's where we calculate up the power transformer needs. So we've got all the tubes written down, and we've got the heater voltages with their amperage draws, and then we've got the high voltage current needs of each of these tubes. And so if we add up that the 27 is 5 amps, the 56 is 5 amps, the 47, we're going to go ahead and pad it a little bit, say 35 milliamps, even though it's 31. We add these up, multiply times 2 for the 2 channels. We need at least 90 milliamps out of the transformer. And all of the tubes can handle 250 volts. So we don't need to be way over that, because then we're just going to be using resistors to drop it down. And that's not what we want to do. So we're going to shoot for a B plus to the transformer that's around 250 volts. So we end up with that at the tube. And this was a neat little calculation that I pulled out of that 1930s tube manual of how to calculate the cathode resistance to get the grid voltage where you want it. And I just pasted that into this Word doc so I wouldn't lose this, but this is a handy little thing for calculating up what the size of the resistor should be to get the desired grid bias voltage out of a tube. So now that we found this, we know we want 250 volts, we need 90 milliamps, and then we'll come back and revisit this heater voltage. So the next thing I want to show you is this PSU power supply simulation tool that I really love. And it really makes figuring this stuff out so much easier than trying to calculate this stuff up by hand, and it also is a lot more accurate. So first we're going to open the file, and they have a bunch of defaults here that you can choose between, like if you want to have a choke input, filter and start from there. Here's our tube 5AR4 with a choke input, and maybe in another episode I will really do a deep dive into this software of showing how to do, like if you're going to do a solid state one. So here's the power supply I initially drew up for this amplifier, and here's the specs on the choke that we're going to be mounting on the top of the chassis. And it's a 5 Henry with a 65 ohm DCR, or DC resistance. And I'm also going to add a 2 Henry choke inside the amplifier that has a 57 ohm DC resistance. Okay, this old tube specifies that this first capacitor after the rectifier tube should be a 4 UF. And I'm going to go ahead and show you how to, I'm going to change this to a common value that's available today, which is a 4.7. Then we're going to have this choke. Because this is a really old rectifier, I'm going to limit the second capacitor to a 47 UF. And then we're going to put this second choke and then put a 150 UF after it to do some fairly serious filtering to get the ripple down as low as we can. So you can see this is a full wave rectifier. It's got two diodes. We use the center tap as the negative side of the power supply. So here's our load, which is the output tubes, which is 65 milliamps. And then to simplify this, I'm just going to show one of the drop-in resistors and then the decoupling capacitor with the load. And we could come back and calculate up even the second tube when we get to that point. So let's simulate this and see what this gives us. The other thing to note is this voltage on the transformer. That's the voltage from the center tap to the outside winding, not across the whole transformer. So this 275 volts is a 275, 0, 275, or a 550 volt power transformer. So we're going to simulate this. So this is showing you the voltages, the voltage swings, all that stuff at different points throughout the power supply. The main thing that we're interested in seeing is at I1, which is right there. Now this looks like you're going, whoa, look at all this voltage swing. Look at these numbers here. It's 250.805 and this is 250.809. So we're in the hundredths of a volt of swing or ripple that we're going to see on the output. That's absolutely nothing. So this is a super clean output. We've also got a standard size transformer, 550 volt, that we're working with. So this is something that's easily found. These are stock made chokes. These are commonly available capacitor values. So this is going to be an easy to spec and source power supply. And it comes right at 250 volts, which is what we're wanting to see. Now, when we get into working on this and build this, if the actual voltage is higher than what we're looking for, and we feel like there's a problem because we're exceeding the maximum for the tube, we can come back here and change this second choke to one with a higher DCR and maybe a 3 Henry with 100 ohms DCR, and that will bring down, let me just show you what that'll do. So let's change this to a 3 Henry and something more around 100 ohms. We can simulate that. And that brings it down to 247. So you can do some tuning here, and if we need to, we can add a resistor to this choke, a power resistor, to get the voltage in check for what we need. But I wanted to show you this software and to show you how easily we can design a power supply that's going to be pretty accurate, which we can come back and revisit when we get a little deeper into the schematic and figuring out how we want to do things. We're going to go to Hammond's website. And while we're here, let's look at the chokes. Just to get an idea here, if we need to change the DCR. So the one I'm going to start with is 157R, which is a 2 Henry, 200 milliamps, which is way over what we need. And it's got 57 DCR. If we do need to lower the voltage, we could go down to this 154M that's 100 milliamp, but it's got a 175 DCR. So if we end up with too much B+, we can always switch out this second choke, and that will add the resistance we need without having to just stick a power resistor in there that's going to generate a bunch of heat. So let's go back and look at our transformers. And there's two different ones. This is the cheaper 200 series that has fairly limited capabilities, but they're less expensive. And these only work in the US. So let's go back and look at this version. And these are a little more expensive, but these have all sorts of primary windings that you can play around with in parallel or in series to get the voltage that you need. We also have a 50 volt that can be used for the grid negative bias for our output tube, and all these secondaries are center tapped. So if we go here to this 550 volt 144 milliamp, we get the headroom on our rectifier tube, which is nice to have. So this transformer also has this 6.3 volt center tap at 4 amp. And so if we add up the two 27 tubes, we come up to 3.5 amps, which is under this 4 amps. So we should be able to drive the filaments of both of the 27 tubes off of this center tap 6.3 volts. So I think I'm going to order one of these 370 EXs. We still need to power up the heaters on the 47 tubes. And if we were going to go with a cathode bias, which we possibly will, they each will need their own winding. So I think we want to go with this model here. So the two different options we could do, if we were going to run them as fixed bias, we wouldn't need separate transformers to power the filaments because the center tap of the filament is going to be grounded. But we may end up going with cathode bias, and I want to be safe here. So I think what I'm going to do is order a pair of these 166 L2s that gives 2.5 amps. Each tube needs 1.75, so this one's not quite big enough. So then we can pull the signal off the center tap of the transformer, and if we decide to go with cathode bias, we're not going to have an issue with that or signal crosstalk. The other thing we still need to do is we may need to have a transformer that can power up the filaments of the 56 tubes if we decide to add them. And so we may go ahead and just get 3 of these, and that gives us the 2.5 amps that would cover both the filaments on the 56 tubes if we decide to add them. So we could end up with a whole bunch of transformers underneath this amp, but that's one of the things I said that's a problem with these 2.5 volt filaments is they do take a lot of amperage to drive them. Well, I hope that gave you a little insight into my thought process on how I come up with a plan, schematic, and design for one of my amplifiers. And I hope you will excuse my voice today. Had kind of a coffee mess of a allergy something going on. And I'm feeling okay today. I was feeling bad yesterday. But anyway, I know I sounded a little froggy on some of this earlier and was coughing and stuff, which I edited out. But anyway, got the transformers ordered. All that stuff should be here in the next couple of days. 3 days probably at the most. I want to thank all the people that have made some donations lately. That's given me the ability to order parts to get this amplifier built and move on with some fun stuff with this channel, which I think a lot of you are enjoying. So thank you for that. And I'm going to wrap this video up right here. So if you're enjoying this content, please sub to the channel. Please like the video. And we'll see you soon for some more 47 tube amplifier fun. Have a great day.